Okay, so I hope you all are ready to fly through the solar system. This is a very broad topic, so I'll do my best. And if I take too long, we'll drop off the boring, puny aurora planets at the end. So, to kind of organize my thoughts, I decided to make a little auroral scorecard for the solar system, and you can see how it comes out. What do we need to make an aurora? Charged particles, they need to have enough energy, a neutral gas and atmosphere, and the charged particles collide with the neutral gas, excite it, and then it glows. Usually the charged particles in classic aurora are energized by a magnetic field and associated currents and potentials. Now, instead of going from Mercury out and starting with something that's kind of boring, I took the invited speaker's prerogative of inventing my own classification scheme, and using a typical scientist's hubris, I used my own initial as the organizing letter. And so I'm going to sort of organize it by Aurora Classic, which you're all familiar with, and then a small new class of Aurora Classic, New Aurora, and then Puny and No Aurora at the end if I have time. So bear with me, we're just going to dip our toe into the vast auroral ocean, and it's a very high-level introduction, and many following speakers in the next day and a half are going to take you to a more depth than I'm going to. So starting with the Aurora Classic, the big three we all know and love, the Earth, which I really love. I've always loved the images of the Earth aurora from outside the Earth, Jupiter, and Saturn. Now, this diagram's been talked about, especially for the Earth earlier this week. One of the things that really helps us understand those three planets in a comparative sense is a simple model prediction of the cold plasma flow that's produced by adding the solar, wind, and rotational electric potentials. And I believe, if I understand the pedigree of this diagram, it was provided by Tom Hill for a review that Barry Mock wrote for the Saturn book. And I also like, pointer, no one told me where it was. Top button. Okay, so the Earth. The inner line shows the plasma pause, the magnetopause, and how rotation compares to the solar wind field. And so a simple thing we learned quickly is that for Saturn, it's relatively rotation dominated. For Jupiter, it's almost completely rotation dominated, and for the Earth, it's our familiar pattern that's solar dominated. I like this version of the diagram that shows the plasma pause and the rotation compared to the plasma pause that Cheng and Kermit just did, because it shows the Earth and Jupiter together, and you can see then easily, first of all, where it crosses for Jupiter, which you can't see on the other diagram. But so it's just, even with this simple model, we get the basic picture that the Earth's auroral system and magnetosphere is solar wind driven. Jupiter's has, as Fran so eloquently explained, has strong internal sources and is rotation dominated, and Saturn is rotation dominated but turns out to be a bit of an intermediate case. Now, I've listened all week long to people talk about the Earth, and I've been so impressed with how well we understand it. And so I was just really happy to find this diagram by Ray and Ergen that illustrated to me what you all have been saying all week, and that is that the Earth is really simple and we understand it really well because we have lots of data. So I'm not going to waste any time trying to talk about Earth aurora to this crowd because I don't know very much about it. You know way more than I do. So we'll skip on to the things that I know a little more about. And another beautiful diagram from Ray and Ergen that Fran, talked a little bit about is that Jupiter and Saturn are very complex because they have strong internal sources, they have strong current systems connecting the satellites and the planet, and that creates a lot of interesting effects. So the reason I deduce that the reason there haven't been many Jupiter Aurora talks or many planets talks in previous early Chapman conferences, Yosemite Chapman conferences, was that in 1974 and 1976, we really didn't know anything about the Jupiter Aurora. We knew that there were radio emissions, we knew they were modulated by Io, we knew there was a strong magnetic field and suspected there were aurora, but the UVS observations by the Voyager mission gave us the first really crude diagrams where the dark dots show where they see emission, the open dots show where they didn't see emission, and so you can get a very crude boundary of the auroral emission, but it's pretty crude. So by early 1990s, we improved a lot. These were the first UV images taken with Hubble. This was a very early camera for Hubble that didn't have nearly the UV sensitivity that later cameras had. But at the time, I remember just being thrilled with being able to image the aurora, and it was always my dream that we would see the kind of Dynamics Explorer's images for Jupiter that we had for the Earth. And that actually happened relatively quickly. And now, you know, these are sort of iconic images that I think almost everyone has seen. And so what I'm going to do is talk a little bit about the morphology from these two UV electron-excited atomic hydrogen and molecular hydrogen emission and the ionospheric ground-based IR-H3+ emissions. I'm going to talk a little bit about the morphology, and then I'm going to show you a few movies in which I hope that you can see many of the features that I'll just describe here with the static images. So there are sort of three main emissions in the Jovian aurora. By the way, this is the North Pole. There are the satellite footprints, and here we see Io, Europa, and Ganymede. The satellite footprints are fixed at the magnetic footprints of the satellite, so they don't rotate with the planet. And this is very powerful because it provides a fiducial for the location of the magnetic field near the planet, and it allows us to map the other emissions to their location in the magnetosphere much more accurately than we could without the satellite footprints. So the footprint mapping has revealed that there's a localized region of low field strength in the northern hemisphere on Jupiter, sometimes called the magnetic anomaly, and if you know Alex Dessler, we always called it the Dessler anomaly. The locations of the other emissions, I already mentioned, can be located accurately in comparison with the satellite footprint latitudes. And the other thing that's interesting is Fran showed you the flapping plasma sheet at Jupiter. The satellite footprints show a persistent pattern of increased brightness when the satellites are near the center of Jupiter's current sheet. But one interesting thing about that is that the scale height you derive from seeing those brightnesses vary isn't really consistent with other measurements, and so that's an interesting thing to pursue. Then there's the main oval that we know and love. The main oval emissions do rotate with the planet, unlike the Earth, where the main oval is approximately fixed in local time. As seen from Earth, Jupiter has a highly nonpolar and tilted magnetic field. As Fran mentioned, it's tilted 10 degrees, and that carries the auroral zone in and out of the line of sight, as seen from the Earth as the planet rotates. And so the overall power of the aurora on Jupiter is driven mainly by the brightness of the main oval. The north oval is sort of kidney beaned in shape, and you'll see that better later. And the magnetic field is near one end of the kidney bean. The southern oval is smaller and much more symmetrical, and it has been studied a lot less because it's harder to see from the Earth because it's smaller. The main oval, as we'll see later, maps to the middle magnetosphere, and the cause of the main oval is the breakdown of co-rotation at that distance. The ionosphere of Jupiter loses its grip on the plasma, and co-rotation breaks down, and that causes the process that gives us the main auroral oval. The main oval is fairly steady on time scales of minutes to hours. As you can see, it's narrow and well-defined at dawn, and breaks up and becomes less well-defined in the dust sector, and Fran talked a little bit about why we think that might be. There are extremely bright auroral emissions that are frequently observed along the dawn edge of the main oval, and you'll see one of those in the movie. The dawn storms can rise to several megarayleigh over a period of about an hour and persist for a few hours. They're fixed in local time, so they remain centered along the main oval near dawn while the other main oval emission features rotate past. And so that tells us that it has something to do with the solar wind and not an internal source. The polar emissions are complex and highly time variable. Polar flares rise from near background to tens of megarayleigh on a timescale of tens of seconds. excuse me, then fade away on a somewhat longer time scale. They often appear near local noon. I should have brought my water up here. And then I love the quote from Peter Delamere in his chapter in the AGU monograph book was, poleward of the main oval is an apparent battleground where the control of the polar region cannot be clearly delineated between the solar wind and the rapidly rotating magnetosphere. So now, I should mention that there are, oh, thank you so much. There are also sort of copious X-ray emissions, and I'll show a movie of that later. And I believe that Tom Cravens will talk about that. I think it's later today or tomorrow, I don't remember. Okay, so the first is a UV movie of UV images, and you see a dawn storm here along the main oval. You'll see the polar emissions, and there was a flare around noon. You see the main oval's less well defined as you go to the dusk sector. Maybe I'll just show it one more time. So that's why I told you what to look for before we showed it, because you have to be on your toes. So maybe I won't show it again. Okay, I won't show it again. Here are the X-ray emissions, and this shows a bright polar flare in both the north and the south. I hope you got that. Sorry, I should have prepared you a little bit better. And then taking these many images, now just doing a polar projection, and so we're looking straight down on the North Pole. There's been a tremendous amount of detailed work done trying to understand where these different regions in the auroral emissions map to in the magnetosphere and what it means. And so in addition to the things I've described, especially with the ground-based H3+ spectroscopic observations, you can lay a slit across the emission and you can get velocity information as well as brightness information. And what we see is that in addition to the things I've described, there's a dark region in the polar area that is stagnant, sub-co-rotation. In the IR mapping, that's been called the, and I also should have mentioned, it rotates with the planet, and that's called the I think that stands for rotational dark polar region. And then there's a part that's fixed, and it's called the fixed dark polar region, or also the swirl region. The active region is where we mentioned that there are often polar flares at noon, at local noon. And so this kind of detailed mapping has really gone a long ways in telling us what the magnetospheric locations are for the sources for the emission in the aurora. And here's an example from Marissa Voigt's work, just to show you how she's mapped different locations in the magnetosphere very carefully to the polar ionosphere of Jupiter, and she's done it for compressed and expanded magnetospheres. And from that, her conclusion is that Jupiter has a fairly large polar cap, which is the dashed pink line here, and the rest of this area in here is open field lines, and then of course we've already mentioned the closed field lines in the current system connecting to the co-rotation breakdown area. And Fran talked a little bit about, we'll leave Jupiter with a brief view at that, but some of the open issues, and probably one of the most fun ones, is that because the emissions fill the polar region, identifying a true polar cap is very difficult. And so I think people have done a fantastic job of really trying to identify the magnetospheric mapping, but still, one group argues for a relatively large open polar cap, while another argues for a relatively small polar cap region with a viscous solar wind interaction that Fran described in some detail. And so that's actually one of the fun, outstanding problems that there's a lot of discussion about. The other thing is that even though our simple model told us that Jupiter's a rotation-dominated system, the solar wind clearly still has an influence on the main oval, even though it's thought to originate very in the middle magnetosphere. So let's quickly dash on to Saturn, and I'll do the same thing for Saturn. Not quite as much information about the Saturn, but I'll give you a little bit of information on the auroral morphology, and then I'll show you a couple movies. So at Saturn, Cowley and Bunce in the early 2000s calculated theoretically that the field-aligned current system wasn't sufficient to enforce plasma co-rotation at Saturn, and that the associated field-aligned potentials aren't sufficient to produce the observed auroral brightness. And so, you know, we already thought it was a solar-dominated magnetosphere, and that reaffirmed that thinking. Now, Saturn's auroral emissions are much fainter than Jupiter. They've only been very hard to observe them in the IR from the ground. The morphology is dominated by a main oval, which is often not symmetric, and you'll see that well in the movies, but it's more or less centered on the very closely co-aligned rotation and magnetic axes. It's nominally located near 75 degrees, but it drifts a lot from day to day. The oval's also offset about 2 degrees toward midnight and about 1 degree toward dawn. The oval, very interestingly, has been seen to wobble around the average center location with a period consistent with the Saturn kilometric radiation rotation period. And I'll talk a little bit more about that with one of the movies. Also, bright emission regions observed along the ovals come and go on a few-hour time scale and appear to move at a fraction of Saturn's rotation rate. So, evidence of the strong solar wind influence at Saturn are shown nicely in some work in Bill Kerr's chapter in the Saturn Cassini book. And the HST UV images show the onset of an auroral storm. At the same time, the solar wind measurements show a big increase in some shocks in the solar wind, and the Saturn kilometric radiation responds at exactly the same kind of at exactly the same time. So from combined observations like these that have been done a lot and are actually ongoing now, we know that the UV and Saturn kilometric radiation are correlated with solar wind pressure, and the auroral wind brightenings at times of solar, the auroral brightening happens at times of solar wind shocks, which is consistent with the picture that I've talked about. So this is a video that was released yesterday. And so this will loop through twice. The first time it's sort of unannotated, so just enjoy the view, and then the second loop through it explains what you're seeing. So you start with a dawn storm. That's one thing I wanted to point out because it goes really quickly. So those are the HST UV images. These are Cassini UV images as Cassini flies over the pole. And these are Cassini infrared observations. So it's going to loop twice, so I'll drink my water. So it's fun to see the structure along the oval and how it changes. A little bit more Earth-like, a very well-defined oval. Okay. Sure what happens if I try to move it on quickly. So, I think that gives you a nice view of the morphology of the sort of nominal aurora at Saturn. But of course, things are not always as simple as they first appear. And so, though we think Saturn is a solar wind-dominated system, this is a nice movie. See if I can get it to go again. Yes, of auroral UV emissions in the center that have been expanded a little bit just to make it easy to watch. Energetic H+ ions observed with the energetic neutral camera on Inca on Cassini, and then the Saturn kilometric radiation down here. And I hope you were watching. I didn't talk before I started. I should have talked before I started the movie. But what you saw was the ions brighten at exactly the same time that the aurora brightened. They're both rotating. And then at exactly the same time, the Saturn kilometric radiation bursts. And so this is work by Don Mitchell. It was published in 2009. And the CD for the Saturn Cassini book actually has this movie on it. The ENA image, protons and ions, well, so what's really interesting at Saturn are that there are a number of phenomena that are linked with Saturn's rotation. And somebody talked about the Saturn plasma cam the other day. So protons and ions are periodically accelerated once per Saturn magnetospheric rotation, usually in a similar location in the midnight to dawn sector at a radial distance of 50 to 20 RS. And so Mitchell et al. Suggests that that acceleration is related to reconnection and plasmoid formation in Saturn's magnetotail. And so perhaps that's an explanation of what's going on at Saturn. The bottom line is that both Jupiter and Saturn have characteristics of both internal rotation dominated and external solar wind driven. Okay, so now I'm going to have to hurry, and I'm for sure going to have to skip the boring stuff at the end. So the new little brother in classic Aurora is Ganymede, which one of the most magnificent discoveries of the Galileo mission was the magnetic field at Ganymede, which is illustrated here, where the background Jupiter field is the dashed lines. Ganymede's open field lines and closed field lines are in green, and then the separatrix is this dark red. And then Hubble images of Ganymede showed bright polar aurora. This is atomic oxygen emission that's excited by electrons from the Io-plasma torus that have diffused out. But the exciting thing that's happened recently is several years of observations. If you put them together and you have different views of Ganymede, so this is the geometry of the observations. Here we see the upstream hemisphere as Ganymede orbits around and comes close to being eclipsed by Jupiter. We see the Jupiter-facing hemisphere, and then on the other side of Jupiter, seen from Earth, we see the leading hemisphere, the downstream plasma hemisphere. These observations are made over a number of years, but two sets of observations of exactly the same hemisphere made 4 years apart show almost exactly the same morphology. And so what we conclude from this in a couple very new sets of observations is that Ganymede has an extremely stable auroral emission pattern, and you can now map the location of it. These are sort of the crude Ganymede maps that are like the old Voyager maps, and you can get rough ovals. And you'll notice that the northern oval is much bigger than the southern oval, just like Jupiter, probably completely unrelated, but it's kind of an odd coincidence. And another thing is the northern oval is skewed. It seems like a little bit oriented, related to the Ganymede magnetic field. The flow is going from right to left here, and you can see that the oval isn't symmetric around the plasma flow direction, and it's not symmetric around the pole. And there's been beautiful modeling done by Xuanji, and this is what the models look like, but the wonderful thing is they match the data extremely well. And it's really pretty miraculous because these models are geared to match the Galileo magnetometer data and haven't been tweaked at all to match our data. And so we were astounded and really pleased that we can do a good job. Now, Fran talked a little bit about the other satellites that I call New Aurora category, and I love the quote from the Mach and Bagenal chapter in the AGU monograph book is that one of the wonderful aspects of non-terrestrial magnetosphere systems is the presence of electrically conducting satellites that provide a whole new set of auroral systems. And so these are objects that have quite tenuous atmospheres, but they're dense enough. They're collisional, they're dense enough that they have conducting ionospheres, and so these objects are neutral plasma and neutral particle injectors immersed in a giant magnetosphere, which, as Fran talked about, generates a very strong current system. Io has an atmosphere of SO2 produced by sublimation and volcanoes, and the strong current system, Fran talked about this in detail, the interaction. You saw what happens at one end of the interaction. You saw the footprint in the Jovian aurora. At the other end, Io has a very rich emission line spectrum of sulfur and oxygen emissions that are excited by plasma electron impact in that interaction, and that's what we call aurora. You can image any one of those emission lines, and this happens to be the oxygen line, and what you see for the aurora on Io is that it has bright spots that are fixed at near the equator. You in visible, in UV, in IR. But the interesting thing about the spots is that they rock in concert with the orientation of the background magnetic field. And so you can think of that as sort of the anchor points for that strong current system and the Alphane wings that connect Io to Jupiter. The models that have been done for this interaction actually work extremely well, which is very gratifying. And so quickly, I'm just going to do Europa and Enceladus, and then I'll stop. Europa has an O2 atmosphere that's produced by plasma sputtering of the icy surface, so a very different production of the atmosphere than Io, but it also has a conducting ionosphere. Fran showed the plume observations. These are the normal aurora. This is a different oxygen emission line that doesn't show the plume, which is why we knew the plume is probably water. But the interesting thing here is that although the models predicted that there would be hard to see kind of spots like Io because the interaction is somewhat the same, just a little weaker, but that's not at all what we see. Instead, we see these sort of little caps of emission that, again, rock with the orientation of the background magnetic field, and in some cases really look like sort of classic aurora. That looks very much like the first Ganymede image. And then finally, Enceladus, with its plume, has sort of an atmosphere of sorts, a large neutral cloud, and it too has a strong interaction with Saturn, and the Enceladus footprint has been discovered recently. So I'll stop there, but somebody has to ask me a question about Mercury, so I can do a nice transition to Jim Slavin.
I wasn't going to ask about Mercury, but I did want to ask about Saturn and maybe Jupiter. You mentioned that the wobble of the aurora is coordinated with the SKR. Does that share the difference between the hemispheric difference that is seen in the periodicities of the SKR?
Yes, it does.
Excellent. Great.
Yeah, it's pretty weird, isn't it?
Yeah.
It does.
I'll ask Mercury after I've asked my first question.
Okay.
Or made a comment, actually. You made the comment that the dawn storm suggests solar wind control. I'd like to remind people that the first thing that the solar wind does, it makes a sunward, anti-sunward asymmetry of the plasma and field environment. And in a rapidly rotating planet, that makes a very, very strong east-west asymmetry in the plasma and field properties. So I don't think that the statement that the solar wind is responsible is probably has to be modified by saying that the dynamics may still be internal.
I guess it was too strong of a statement. I would say solar wind related. How's that? Is that a better way of putting it? Okay.
Okay, as long as everybody knows what it means.
Okay.
And can you tell us something about Mercury?
Okay, okay, if you watch really quick, you can go quickly through all the puny aurora. Mars, boring. Uranus and Neptune, really weird, really weak. I hardly even call them aurora. Neptune, barely detected. Venus, they call it aurora, but come on, thumbs down. I don't think so. But I would just say quickly that I think Venus, Titan, and Callisto are very similar in that they have very conducting, thick, dense ionospheres that stand off the plasma, and so you really don't see emissions. But Mercury, and many other rocky bodies, they have, if you want to call it a tenuous exosphere, something, anything that hits it knocks stuff out. And you can see that stuff. Many elements glow by solar fluorescence, but it doesn't have a conducting ionosphere, and the atmosphere is way too tenuous to produce aurora. And I know Jim's going to talk a lot more about that, so I thought it would make a nice segue.
Actually, I remembered I had a Jupiter question too. You mentioned this flaring in the polar cap aurora. Is that possibly due to like bursty reconnection or something like that, or is there some other mechanism involved with that, or is it not known?
Tom, you're going to talk about that, right? No? Okay, so it's a totally different process than you're seeing for the UV emissions. It's more related to ions and Bremsstrahlung emission. And so I'm going to let Tom talk about it from there because he's actually really an expert on it.